This is my presentation. It's about impact on the floating ice. But as Vernon said, it's not actually about ice, it's about elastic plate. And linear elastic plates, there are no nonlinearities in terms of the structure. This research was supported by Office Naval Research for several years, and contribution from Tatiana Khabakhpasheva is significant. All results and almost all pictures from her. And also Kevin McKee, he guided us through many problems. And the results of CFD calculation shown in this presentation they are from him. So this is why the Michigan University is also here. So the motivation comes from the climate change, but this means that this also was mentioned several times that climate change means the ice disappear, but it doesn't mean that it's disappear completely. It's the broken ice, as I understand, amount of broken ice becomes bigger. So, and even you can meet floating pieces of ice much south than, okay, I'm talking about Arctic, much south than they were before, when they are part of the continuous ice. So the motivation is about, in particular, mainly about the safe boats, how to use safe boat in icy water. At present, it's not allowed to use it, and we think it's a wrong idea. In particular, they are at least in Norway, they design new lifeboats, especially for icy waters. But I believe and the results of our research show that the standard lifeboats can be used. And also navigation in ice. Kevin McKee already mentioned this. So that is the channel behind the icebreaker, and you can see it's there almost no open water. So icebreaker breaks the ice, but there is the pieces, and a ship or convoy of ship, they're moving in that broken ice. So there are always the impact between the ship hull and the ice. So there are different types of impact, and one of them is horizontal impact, which is very much studied, in particular because of that periodic forces and on the offshore structure and vibration of that structure caused by that forces. So that is the a lot of research in that field done, but we are studying another type of impact, which is called vertical impact. And also our impacting body is rigid and blunt, means that damage is caused by bending. It's not like that. So we do not consider localized loads. Localized load is another problem. It's not here. So if you ask something about crushing, it's not about this presentation. It's presentation by somebody else. And possibly you remember this figure, but not like this, shown 5 years ago by Haley Shen. No? It's instead of that animals, there were the people and on the ship. No, you don't remember, but I couldn't find it, so I used that one. So the problem is divided. Problem of impact in the presence of ice or on the ice, divided into pieces. So the one of them is impact in the near the floating ice. So that is the relevant in particular to the presentation by Kevin McKee when we navigate close to the ice edge, or slamming of the ship close to the floating plate, and this is the most relevant to the problem of lifeboat. But we study this problem. So its impact exactly on the floating plate. Let's say plate, sometimes I'll say ice, but don't worry about it. I'm not using anything from ice except of the Young modulus and the density of ice in calculations. There is another more complicated case when the impact occur in such a way that the both open water and ice is involved, but this case will be not shown. We'll concentrate on this middle picture or middle picture only. So, and even even this workshop about mathematics, and what we did here is mathematics, but I hope the mathematics is what I will show will be not very boring. And I will concentrate on the results from mathematical analysis, which are not sometimes intuitively clear. In particular, I will explain about the regularization of impact problem, which is, I believe it's not well understood, the viscous effect in impact problem. So we are well familiar about the damping of, because of viscoelasticity or elastic or viscous effect or other effects in wave ice problem, in hydroelastic problem, but not so much in impact problem. And you will find that in impact problem of short duration, the effect of damping is just opposite what you familiar in wave problems. Then about, Then about how to scale stresses and how to treat the impact on the already damaged plate, including the breaking plate into pieces, so it also will be covered. And finally, three-dimensional problems. It's it's very impressive, but it not takes much time because it's absolutely the same as two-dimensional problems in this analysis. So first about the how to regularize the impact problem by introducing soft layer on the top of the floating plate. And that is the scheme from the paper by me, Maki, impact on the ice floor. In this problem, the plate was rigid, and we added the thin layer on the top of it. It's, as was explained in one of the presentation, many small springs which react only in vertical direction. There is no horizontal stresses in this soft layer. And because I said the body is blunt, so it's not like nail, so we can use the one-dimensional Hooke's law for the stresses as function of the say elongation or compression of that spring. So finally, we can use we arrive at the equation that the forces in that soft layer, they are proportional to the indentation of the body in this soft layer. Right? So that is the law of so-called elastic foundation. It's well known, but it's used in different applications. And it's interesting that this law is very simple, so everybody criticizes it, and each month, the people return to that. To this approximation again. The reason is that it's very simple and very understandable, and you can use it to explain others what you are talking about. Right? So if you use something more complicated, nobody would understand you. Okay, if they are, okay. So in addition to Hooke's law, we introduce damping. And that damping, dissipation and tau, it's described dissipation, and tau, it's so-called retardation time of the soft layer. This term describes the dissipation, for example, due to crushing. So by using this term, potentially, we can describe crushing of ice. Or we can this soft layer can be used to model snow, for example, on the top of the ice, or some covers. Sometimes in some technologies we need to cover ice with the plate, and then to make operation on that plate, but not on the ice, because the ice can be damaged. So that is the reason. But also, if you want, you can consider this layer as just regularization of the problem with concentrated loads. And the key point, concentrated loads. Because if there are no that layer, there is no such thing as distributed loads. So if you find the impact problem, we are saying, yeah, the bending of that floating plate caused by some piece of pressure, it's not right, because there is because there is always for model of thin plate, there is no concentrated loads, no distributed loads, all loads are concentrated. First, I'll show the comparison by using this problem. It's impact on the floating rigid plate. So that is the equation of the plate motion. This is the equation of the impacting body motion, and that is equation for the plate indentation by using the model I showed. And that is the results, theoretical results, by integrating of these second order differential equation, just 3 differential equations, and by CFD. This calculation done by Kevin McKee and his PhD student. And you can see for velocity of the body, velocity of the plate, the theory and CFD give very close results, right? So this in particular means, as in many impact problems, viscosity, gravity, surface tension doesn't matter. And it's only inertia, mainly inertia. However, in impact problem, coupling between elastic deformation and loads, very important. Right? And this is problem, Kevin could confirm, problem for CFD. It's still complicated to solve hydroelastic problems by CFD in a reliable way. Right. So he's confirming. So if the ice is small, then the problem becomes more complicated. So you see there is ice, then it's appear on the bottom of the body, and there could be another piece, and then they come together. So that is complicated, but it's possible to describe it. And these pictures, they are inspired by presentation 5 years ago by Hooke. You could remember you showed the bottom of the ship from below, moving in broken ice, and it's just covered with ice. So ice is not going aside like in discrete element model. It's also under the ship. So to model this situations, we modify shape of the floating body or shape of the entering body by including this plate. And shape is changing in time, but we can do this. It's not a big problem. If the plate is elastic, so that is the more complicated case, we use the same things. So we introduce also that soft layer, but in this problem, our goal is to calculate impact loads, not to assign them, but to calculate, to compute them, to evaluate them. And to do this, we need that soft layer. Without soft layer, there is only concentrated load. This is the illustration. This is not exactly the problem we study. That is the, it's not about impact. That is the static problem. If we consider floating elastic plate of infinite extent, and we put cylinder on the top of it, you could imagine, I believe all of you agree, that the contact occurs at single point, right? Then, if the mass is 0, so it's no mass, then we increase the mass, and do you expect that there is a contact, contact between the cylinder and the plate of finite dimension? No, it's just the same point. It's exactly the same point, that one. Because the curvature of the plate is smaller than the curvature of the disk. So they always only concentrated loads. And if you increase the, don't worry about large deformation of the plate and the linear theory I use, because this is the vertical axis is scale, or vertical scale, it's much smaller than the horizontal scale. And when we increase much more the mass of that cylinder, then, okay, you also expect that there is interval. No, the one point is kind of bifurcate in some sense, if to say, if to use the complicated mathematical word, into 2 points. See, one point over here and another one over there. If you continue increasing, that each point is bifurcated into 2. So it's always concentrated loads, only point loads. So to simulate these impact problems with a rigid body, numerically, it's very complicated. Actually, it's impossible because you need to describe the loads at a single point. To regularize the problem, we introduce the soft layer. All right, and then equation of then equation of the plate is shown over here. That is the standard equation. We include the viscous term, so that is the retardation time of the ice. Then this is the dynamic pressure acting on the ice. Phi is velocity potential. This is the problem for a liquid of infinite depth and infinite extents, two-dimensional problem. That is the hydrostatic pressure, and that is impact pressure. And impact pressure, this impact pressure we calculate. We do not assign it. So we calculate it by using, in some sense, generalized Hooke's law. The that function g of delta, where delta is relative compression of elastic layer, is describes the property of material. Okay? So we include that this soft layer could be compressed very much. It's not just small compression, and it's described by that function. In our calculation, just was selected. It has no relation to any material, but you can use any other relations over here. So that is the initial thickness of the soft layer, and this is current thickness of this layer. So altogether, it's all called relative compression of the layer. So this is the equation we need to solve. So everything is the same as usual, except of this term, which needs to be calculated. So we need a model for that. It's convenient to introduce non-dimensional variables just to make equation shorter, and then that compression depends on deflection of the plate, so it's everything related. So the impact load depends on deflection of the plate. Hydrodynamic loads depends on deflection of the plate, and deflection of the plate depends on everything. So this is the coupled problem on several levels. That is the deflection of the plate. That is the motion of the body. We assume that velocity of the body is constant, and that is the shape of the body. You can change it. Here it's a parabolic shape, and impact occurs at the point which is not necessarily at the center of the plate. Then we can use the normal mode method. We decompose the deflection by using so-called modes of dry plate in vibrating in air, and all dynamics now in this coefficient an. And if we go to hydrodynamic problem, it's shown over here. So we need to solve Laplace equation in the lower plate. That is the condition on the plate. Vertical velocity of liquid and vertical deflection of the plate are equal. And this is the condition on the free surface. This condition means that gravity is not important in impact problem. The time is too short for gravity, surface tension, and viscosity to start playing a role. All right, so that is the condition, and if we if you substitute W over here, you can find that we can decompose the potential also in some functions which depends only on the modes of vibration of the plate and these part derivatives which are describe the dynamic of that interaction. Then we, from this analysis, we can, in this analysis, we can introduce so-called edit mathematics, which product of the Z potentials, elementary potential, and the normal modes, which this matrix describe interaction of the dry modes of the plate through water, because the plate is in contact with water. So the for dry plates, the modes do not interact one with another, but for when the plate is floating, then they start interacting, and that is the edit mathematics. Right. So the normal mode for the plate with the free edge, no bending. No bending stresses, no shear force. They are shown over here, and some of them are presented there. And they are normalized. And as to edit mathematics, for a floating plate of constant thickness, it's calculated analytically. Results are not shown. That is a special part of our research. Analytically means, it's indeed analytically, it's expressed through Bessel functions. Bessel functions are just J, right? So the actual Bessel function, not modified, nothing else. So this means that these elements we can calculate for large N and K, which is important, and will be used to solve problem for cracked beam. Cracked plate. So finally, once we put everything together, we arrive at infinite system of equations where that first term is for structural mass, that is edit mass, this is about bending, and that is about viscosity, and this is the impact for impact loads from impact loads. Okay. That is the from hydrostatic force. The problem with difficulty, in some sense, with this equation is that the forcing term should be calculated at each time step by integrating the deflection and all other things projected on the normal mode. That is the complicated, but for modern computers, okay, not so much modern computers, but even for not modern computers, it's not a problem these days. And as I said, the elements of the edit mathematics, that matrix, are calculated analytically using the using Bessel functions. They are not shown here, but I hope it will be published. So it's not published. Then, now I'll show the results and discuss the viscous effect in impact problem. So that is the impact on the plate of length 5 meters, thickness 15 centimeters. Soft layer is 1 centimeter on the top of it. Impact by, say, cylinder of 5 meter radius. So that is very blunt body. And impact speed is 1 meter per second. The impact loads, they are separated into elastic loads and viscous loads. Viscous loads is just derivative in time of the elastic loads. And they are shown over here. That is the elastic load for different conditions. So 2 means that there is no viscosity in ice, but there is viscosity in soft layer. 4 and 5, there is the viscosity in both layers, in both elements, but they are quite small. And you can see that always the contact between impacting body and the plate is finite. So it's 0.2 seconds. It's very short. It's nothing happening during this period, except the plate can be broken several times. But the displacement of liquid is nothing. It can be neglected. And this is, and other effects like, as I said, gravity, surface tension, viscosity also can be neglected because it's nothing happening in terms of the displacement during that time. So it's not about the impact, it's not about displacement, it's about acceleration. Acceleration and inertia is the main effects. And how is possible? The body moving down at the and impacting and the at the constant speed, why there is bouncing? So actually this means that the plate, impacting plate, separate from the body, and it separate not, it's not bouncing, it's deflection. it's after the impact, the plate is deflected, and then it starts vibrating, and in this way separate from the body. So there's many things happening. That is the, in red line, the positive pressures are shown, and here you see negative also pressure shown. So the loads calculated with account for viscous characteristic, they give not only positive impact loads, but also negative impact loads. And if you look at over here, the impact loads at the beginning of impact with viscosity, they much higher than without viscosity. So viscosity increases the loads. And this is, my explanation is that viscosity means that there is delay in response of the structure. And because of this delay, initially, when the impact just starts, that elastic layer cannot react immediately. Reacting with delay, and this means that impact happening as if impact on the rigid body, right? And finally, there is also that negative loads caused by delay in the response of the structure. And this is what I told you, how the happening that the body penetrates into the water and plate finally separate from the water. That is for small time, and that is for larger time. So that is due to elasticity. It's not bouncing. It's some bouncing, but due to elasticity. And that is the strains. Strains are too high. It will be shown. Once we analyze strains, we try to find out what the strains are dependent on, and we arrive at this formula for so-called scaled strain. That strain, or maximum, better to say maximum, no, not better to say just maximum strain, they are proportional to length of the plate, impact velocity, inverse proportional to the thickness of the plate. So if you thinking about the maximum velocity which breaks the plate, so we can use this formula. And this comes from the analysis of numerical data, and we find the maximum velocity under which the plate still not broken by the impact. Big VP here is so-called bar speed. It's a speed of compression wave propagation in the material of the plate. So, and that scaling is shown over here. That is maximum strains as function of time, calculated for different velocity, different thickness of the ice of the plate, and then the scaled strains are over here, shown over here. So clearly it's written that the strains are proportional to velocity and inverse proportional to the thickness. And also asymmetric impacts can be studied, just for illustration that everything done but not published yet. So now the impact on the plate with crack, so that is story, right? So if you remember, it's very important, the edit mathematics can be calculated for any number of modes, 1,000, million, any, doesn't matter, because it's given by analytical formula, right? So because of that, we can use this matrix to find, to solve the problem for complicated structures. For example, not necessary, but for example, it's a plate with the crack over there. And to model this situation, we use that the plate is thin, and then we use its much asymptotic analysis. So we can replace the plate approximately by torsional spaying. And there, it's not something special. There are handbooks how to do this. So for different configuration, what's the relation between the rigidity of torsional spring and the thickness of the plate and the length of the crack. So you can find it in that paper, for example. So the rigidity is related to the relative length of the crack by this formula. So then, if we have a crack in the plate, then we consider the plate as two plates connected by torsional spring, and correspondingly the condition of matching at the position of the crack is given over here. Deflection and stresses are continuous at that point, as well as shear force, but the slope is not. So this problem was solved several times, including this case, or very simplified case, when this part of the plate were approximated as the rigid, so the two rigid plate connected by spring and impact on it, and then the length of crack, and but length of crack was calculated. Length of crack was shown to be described by harmonic oscillator equation. Rigidity in that equation dependent on the solution, so nonlinear equation was derived and solved. So that is we can find normal modes. They are over here, and some of them are shown in this way. So that is the lowest mode. There you see they are always the angle, the corner, at the corner n equal to 2, and higher numbers are shown over there. So we calculated that, and then that is the critical point. So we use that as the normal mode for homogeneous plate without crack, and we use these functions to present the modes with the crack, and where C is so-called transformation matrix, which relates different modes. And this matrix actually is not complicated. It's given elements of it given by this formula. So here you can see some results of approximation, and you can see this 50 modes, 50 smooth modes is enough to approximate in a good way the modes with the crack. And then, because we know the edit mathematics for the smooth modes, we can use it in combination with the transformation matrix to find edit mathematics for the crack plate. So it's one crack, it could be many cracks, it could be internal supports, it could be different conditions, plate could be wetted just partly, anything is covered by this formula. So in this way, we find the critical part of the solution, which is edit mass matrix. And then we use that failure criteria, which is, it was mentioned that on the top of the crack, the stresses, they have these asymptotics. I believe you showed it, or where K is the stress intensity factor, and that stress intensity factor, it's within that model of thin plate is calculated, and it depends on the stresses, bending stresses at the same point. It's you can find it in the paper by Marchenko. And the crack is assumed to grow if the that intensity factor is greater than so-called ice fracture toughness, and the results should be here. So in this picture, in this graph, it's shown plate 5 meters long, 15 centimeters thickness, soft layer 1 centimeter. It was also checked that stresses are not so much dependent on the soft layer. So if you change the condition of soft layer, the stresses in the floating plate are quite stationary. And that is the condition. The crack is 70% of the thickness, and it's placed at the point which is 0.2 in non-dimensional variables from the center of impact. So it's over here. And you can see how the plate behaves. It's clear that behaves quite differently from that. The plate is continuous, but because the crack is quite large, quite long. And this is the strains, and the strains are also quite large. And that is the pressures, acting impact pressures. And what's interesting here, that the impact region is not what we could expect in this problem. So it's somewhere, and it has a certain certain shape of this region. So this is the what was calculated. That is another condition when the crack at the very center of the plate, and it's 50% length, 50% of the thickness, and again all calculation done. And here that red line is so-called yield strain. So you can see that if for that condition plate will be broken just at the very beginning of the impact. So when even deflections are so tiny that there are no nonlinearity, there is nothing. It's already broken. Okay? But it's everything coupled. Everything solved after another. And that is more interesting. What's happening after the plate broken? Okay, it's broken into two parts now, but they two parts, they are still there. And body still in contact with them and still penetrating. Then what we are doing, I believe, okay. We solve problem until the plate crack into two pieces. So it's a red curve for strains. And after that, we continue calculations, but we continue calculation with two plates. Right? And with two plates, the stresses at the place of breaking is 0, but they are there. And the strains at the central point, they are increasing in time over here. And then once we come to that failure condition, it goes to 0, right? And we continue calculation. But what we were concerned in this calculation, you see, there is the kind of jump in deflection and even more visible jump in the velocity. Okay, not very big, but still visible. So we couldn't understand. Everything looks continuous, but there is the jumps. Why? Once we go from the unbroken plate to broken plate, we assume that deflection before and after, they are the same. And velocity, they are the same. This is the condition to continue. But it looks like not, and that is a big problem. And we try to analyze it. So we solve this problem as a new normal mode with new edit masses, with account for that plate is broken into two, and then how to break what's happening after the plate is broken into two. And to do that, this is the we were much in hurry to publish these results, and we publish in could be strange journal, because it's like toy problem. It's not so much related to the breaking of floating ice. But in this problem, we considered the plate, it's two-dimensional problem, plate clamped at 2 points, and there is air chamber, and we increase the pressure in that chamber slowly. So the deflection of the plate is static, and we find the shape of this plate just before plate is breaking into two parts. Okay? It's broken in this calculation at that time, and it's happening at the center. Okay? So it's broken, and the question is how to continue this calculation. There are no water. Right? So just a structural problem, how to continue calculating. And we found that strangely, but after it breaks once, the story doesn't continue. Even we do not increase the loads, and loads are uniform, the plate breaks second times, and potentially it can break third times. So that is the problem. It's because after breaking, the plate starts to vibrate, and in some places of the plate, the stresses could be higher than yield stresses again. And we formulated problem after the breaking. It's shown over here. That is the shape before breaking, and that is the condition at the place of the breaking, and that is the condition at the wall. Right? And if we introduce the non-dimensional variables, you see there is no parameters at all except of this one. So if you say there is no viscosity, there is no parameter. But then the problem is too complicated. With viscosity, it's a little bit better. And let me show. But this condition which we use to solve the problem, it seems that this condition is not satisfied. So that is we couldn't solve it. So that is the velocity at the breaking point, that one, as function of time for very small parameter retardation time. And you can see that the velocity at that point jumps quickly from 0 to 4. That is everything non-dimensional. And then we continued calculation, and we showed that it's possible that plate is broken in another place. And finally, it's a three-dimensional impact problem. It's an impact on the floating three-dimensional plate. The calculation done for circular plate, and I believe you understand why. But the theory is three-dimensional and coupled problem of hydroelasticity. So that is the equation of the plate with viscoelastic term, and that is the condition on the edge of the plate, free boundary condition. That is the impact model, the same as for two-dimensional case, but now the shape of the body is three-dimensional. This is shape function of the body. That is the problem for hydrodynamic loads. And in addition, because it's already complicated, what's the point? We can add also equation for the impacting body motion, saying we drop something on the plate and then it could bounce back on doing something. Yeah, and then we, if we introduce the coefficient, I believe Luke showed something like that. If we introduce normal modes of that plate, which are orthogonal, then we can use decomposition of the deflection with respect to this mode, and everything is the same. Finally, even equations are the same. Equations are with the edit mathematics structural term, that is the rigidity term, and that is elasticity, and that is the impact model and impact term, which depends on that our impact model seems the same as in two-dimensional case. But the problem is that these forcing elements we should calculate at each time instance, so it's extremely complicated. Another problem is that these functions they are in terms of their frequency, they are too close to each other. So we need to take many of them. We calculated about 6,000 of that modes. So it's computationally this problem is very challenging. So for circular plate we ordered the eigenmodes in such a way that their frequencies they are increasing. So then, but this means that number of the terms in theta, in polar angle, and number of terms in radius, they are different, because if we limit ourselves to 100 modes altogether, this means we account only for 20 modes in theta and less than 6 modes in R. So I'm not sure that it's a good idea to approximate in radial direction and azimuthal direction separately. Some people doing this, but I don't think it's very consistent. So we put all modes all together and we treat them in the same way. And that is the mode for different numbers. 40 means that it's from first mode is rigid mode and second mode is also rigid mode. One mode is vertical mode and another one is for pitch. And the third mode, actually it means the first elastic mode. So they look like this. That is rigid mode, so no big problem. But what's interesting here, we can manage, because we did something else in the past, we can find the edit mathematics as the singular integral of the product of Bessel functions. And if you're a little bit familiar with Bessel function, you can recognize that this integral is also can be found in tables. So it's shown here just to kind of intermediate, but the product of Bessel functions multiplied by power function, all that products, they are table integrals. So this means, again, as in two-dimensional problems, the three-dimensional problem, but for elastic plate, it's in this problem, the edit mathematics is given analytically, and because of that, okay, some conditions and the calculation were done. Okay, calculation were done for this condition. Sorry for that. the deflections in this direction and in that direction for different impact points are shown over here, so we can do this. And also we can calculate pressures. Pressure is something which is not standard to be calculated in hydroelastic problem, because in coupled problem pressures there is no pressure. Pressure is included in edit mathematics element. So and after that, to return to pressure is very complicated. So we need to improve convergence. We need to go to the asymptotics, but we manage for this, and we need pressure because we need pressure to understand is there cavitation under the plate or not. If there are cavitation, the loads would be different. And also we calculated maximum strains for, in this calculation we need 300 modes and at different time instant. And so thank you for your listening.
Thank you, Professor Korobkin, for the exciting talk. Any questions?
Thank you, that was very interesting. Can you have a rigid body falling on the thing? Can it be considered another ice floe falling on it in some way, just to get some sort of picture of rafting? Or
so I cannot hear
get some sort of picture of rafting as an example. Say having another ice floe falling on the ice floe.
Ah, yeah.
Will your analysis be able to cope with that?
Yeah. Thank you very much. Yeah, very good. Yeah. I'm not to add, but just to say that if you consider rigid body and ice, because I said it's not so much ice, but ice, then the crushing should be included. But I believe the crushing can be included. So this more complicated model of this soft layer, when we allow this soft layer to grow or to shrink depending on the load. So but actually what you said, the impact of elastic bodies, floating body and another elastic body. Thank you.
Thank you, really interesting talk. I was just looking at your equations there in each of the sections, and I noticed you used a particular linear viscoelastic model, essentially the Maxwell model.
Yes.
And I guess I know the answer to this, but I wondered if you used a slightly more complicated viscoelastic model, introducing parallel dashpots or something,
could be
whether that would make any difference to your results.
Yeah, thank you. Could be different, you're right. Could be different. Thank you.
Thank you for your talk. I noticed that you were using a yield strain for cracking.
Yes.
Okay. Have you looked at, or perhaps other people have looked at, using a yield stress for cracking? I mean, if you have a purely elastic body, then there's a one-to-one correspondence. If it's elastic, viscous, or complicated, then a yield stress is what would be more physical.
We use it in just in a simplified way. So that is yield strain is for elastic model, but it's also quite strain different in different papers. We used not for that one, but in some calculations, the review by Erland Schunson, I believe 1990, about that yield strains. As to viscoelasticity, we do not relate the parameter to the yield strain.
Okay, so everyone uses a yield strain in other words.
Sorry?
So everybody uses a yield strain, it sounds like.
But we use the we use this strain. But as to viscoelasticity, that is because that parameter retardation time, we also just kind of assign it. We didn't use actual parameters. We did not use the actual values of retardation time. So let me show. Just a moment. That is. Okay. That is the retardation time. So that is the this term describes viscoelasticity, right? And for this tau, we assumed this is small. So it's see, oh, sorry, oh, yeah. You see, oh, sorry. 0.01, 0.01, so very seconds, very
Oh, I
small.
see. Okay.
Because in experiments, this parameter is used to kind of feed experimental data. And in some experiments, we came across it's 10 seconds. So it's very large. So this very large. So we did not use it. We were kind of close to the elastic case. But viscoelasticity was used in some sense as kind of regularization in some sense of the problem. So the physics should be still brought to these results.
Okay,
It's
thank you
not
very
there
much.
still yet. Sorry. Yeah.
Any more questions? No? Okay, next, it's the morning coffee time.
Coffee time.
Yeah.
Thank you very much.
Welcome back on 11 o'clock.
11 o'clock.
Yeah, there will be 2 more talks this morning.